And now it's time for My Ferrari is Rusting, a presentation on rust, where you'll find out why driving your Ferrari like this, without treatment, could lead to unwanted rust. So what is rust? Rust is iron 3 oxide and forms on both pure iron and iron alloys when exposed to both water and oxygen. An alloy is a mix of a host metal and one or more other elements. Rust can be hydrated or dehydrated. When it's hydrated, it simply contains water. And not all metals rust, only iron and iron alloys are able to rust. Other metals can corrode, but this is not the same as rusting. And if you're a superhero guy, you'll know that Iron Man's suit is not actually made of iron, and therefore can't rust. So what is rust actually doing? Well, this can be explained using the following rusting chemical reaction. And a chemical reaction is the transformation of one or more substances into different substances. When we take iron, oxygen gas, and water, will form hydrated iron 3 oxide, or rust. Here's a quick example of some rust in day-to-day life with a chain before and after rust. And we know now that this will contain some sort of iron or iron alloy to be able to rust. And now it's time to break down the reaction. A chemical breakdown. Okay, so the overall chemical reaction of rust can be broken down using multiple half reactions. And a half reaction is either an oxidation or reduction reaction that's a component of the overall redox reaction. And this basically tells us what's going on in the midst of the reaction. So first, the iron is going to be oxidized, which means it's going to lose electrons. Next, the electrons from this previous half reaction are reacted with hydrogen ions and dissolved oxygen from the surrounding water. And as we heard before, the water must be present for rusting to occur. Electrons are negatively charged subatomic particles that are responsible for the redox reactions when they're exchanged between elements and or molecules. And when something is dissolved, it's when a solid or solute is mixed in with a liquid or solvent to create a new solution. And we're still breaking it down. Next, the iron 2 ions are oxidized with oxygen to form iron 3 ions, and the oxygen is also reduced with water to form hydroxide. When something is reduced, it gains electrons, which can be very confusing to a lot of people, myself included, because when something is reduced, you'd think, oh, it loses electrons. Nope, not quite. Which is why we remember oil rig. Oxidation is lose, reduction is gain. Anyhow, now we have all the parts we need. Now the iron 2 ions are going to react with the hydroxide to form green rust. Our final product will be a red rust, but this is just kind of a little interesting side note. And the iron 2 ions are going to react with the hydrogen ions and dissolved oxygen in the water to form iron 3 ions and water. I'd show a little more, but that darn box keeps popping up. So we're done with everything now, right? Not quite there, cowboy. Our final product is when the iron 3 ions react with the hydroxide ions to form hydrated rust. And this is our final product. Once again, that whole final reaction is iron, oxygen gas, and water to form a hydrated rust. And once dehydrated, the simpler chemical makeup of rust is shown here, but for our purposes, we're going to stick with the hydrated, which just, again, simply means it contains water. But what does this chemical equation actually mean? That's a great question. What this is saying, we can look at the coefficients first, is we need 4 iron atoms, 3 oxygen molecules, which we know oxygen is diatomic because it exists in pairs when it is in gaseous form, and 6 water molecules to form 4 molecules of rust. And our module objective that will be covered in the coming slide is determining how much of a substance will react, what the limiting factor is, and how much product will form as a result. So here I've wrote out a little example we can do. Let's say we have 20 moles of iron, 20 moles of oxygen gas, and 20 moles of water. Doing simple calculations, we can figure out how many grams of each substance we have. And we know, based on these amounts, that water here is the limiting reactant, and therefore we're going to have leftover oxygen gas and iron. The exact quantities are shown here. We have all of the water used because it's the limiting reactant, half of the oxygen gas used, and 2/3 of the iron used, which these quantities are found by multiplying the the weight of the substance that we have by the coefficient fractions here. So we've got 2/3, which is 4/6 reduced, and 1/2, which is 3/6 reduced. So in the end, after some more math, we find that with 20 moles of iron, oxygen gas, and water, we will come out with 1,424.8 grams of hydrated rust. So what stemmed my curiosity and frustration with rust was when I first moved down to Florida for school and found one morning that my brake rotors were covered with little speckles of rust. And I thought it was an issue. I'd never seen that before. But soon I realized, after some research, that this is due to the friction between the brake pads and the rotors breaks down small layers at a time of the brake rotors, exposing the metal to both oxygen and humidity in the atmosphere. And we know now oxygen and water are needed to form rust, which obviously now we know that there's some form of iron or iron alloy in brake rotors. This is completely normal, and most cars down in Florida will get this pretty frequently, and I'll explain that again in a minute. So why is my Ferrari rusting but not my jet? That's an excellent question, and I thought you might ask. So, when you apply the brakes to your car, the friction between the brake rotor and the brake pads is gradually wearing off small layers on the brake pad, which will expose it to the surrounding atmosphere, which contains humidity or water and oxygen, and the iron alloy in the the brake rotors to create the rust. The reason your airplane doesn't rust is because it's made from aluminum, not iron, and we now know that only iron can rust. Aluminum is also very light, which is another large factor for why it's used. And the salt exposure during the winter and or living near the ocean is what causes the outside, any sort of treated layer of of metal to be exposed to the surrounding atmosphere. Salt doesn't cause rust, but it will corrode away a layer to expose the metal underneath. Just going to let this sink in for a minute for you. All right. So the rust isn't necessarily bad on your car. If it's on your rotors, it's going to go away pretty quick, but underneath, not so good. If your brakes look like this, you need not worry. If the underside of your car looks like this, that's probably looking time to get a new vehicle, because this is when it gets dangerous and it starts to chip, and we don't want any of that to cause any accidents. Now's the time to worry. The way to prevent rust, simply wash it, take care of it, wash the underside, and make sure the salt doesn't have time to build up and corrode away that metal. Or the iron and iron alloy. Frequent washing underneath, make sure the salt is off, and storing in a drier place to make sure that you just prevent as much humidity exposure as possible. And now that you know all this, you can buy your next Ferrari with confidence. Cool thing I found the other day, I was hiking by Lake Michigan and I found this rock, and I noticed that there was a lot of rust around it, but then there was this kind of original color in the middle. And based on my past research for this project, I could pretty logically conclude that there was some sort of iron or iron alloy in this rock. And as its location was right by the water, and obviously there's air from, well, the atmosphere around it, that there was some sort of chemical reaction going on in here to form the iron inside or around this rock to form into rust. So I thought that was kind of cool. And here are sources from my research and sources in chronological order for the images on each slide. I hope you enjoyed this presentation, and I hope it will help you in purchasing your next Ferrari.